Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to figure out what the rate law of this mechanism is, as well as what the overall rate of the overall reaction is. So let's get into this. So oxidation of NO to NO2, one of the reactions in the production of smog, appears to involve carbon monoxide. A possible mechanism is the following. So we have carbon monoxide reacting with OH. And so I want to point out here some of these substances have a dot there, like a one dot. If you have a substance that has one unpaired electron, or maybe several unpaired electrons, but usually there's just one unpaired electron in the formula. If you have something like that, that's called a free radical. They're highly, highly reactive. So you don't want free radicals in your body, right? Because they'll react with whatever's nearby and break up molecules and things like that. So that's what these are. These are free radicals. And also, I want to point out that the OH radical here is very common in atmospheric chemistry. And so, again, this usually happens during the light time. During the daytime, it uses UV light to get it to go and continue to go. So it happens during the day. So that's just an intro to free radicals and what these dots mean. So that's an unpaired electron on a molecule. That's a free radical, highly, highly reactive. Okay, so here we have the mechanism, and we're asked to do two things. One, write the net chemical equation for the reaction. Two, assume the first two reactions reach a rapid equilibrium, and the third reaction is comparatively slow. So let's go ahead and put that in. So we'll deal with that later. So these are equilibrium. So we'll have uh, a reverse arrow along with the forward arrow, and these are fast. So fast, and this is fast, and this is slow. Okay, so then they want us to derive the rate law consistent with this mechanism. So with the understanding that these two will reach a fast equilibrium and this is slow, what's the rate law? Okay, so we'll get to that in a second. But first we need to write out the complete overall reaction, adding these three together. So let's go ahead and do that. So what you'll notice here is that we have hydrogen as a radical here as a product, but we also have hydrogen as a radical here as a reactant. So that is going to cancel out. That's not going to be part of the overall reaction. So those will cancel out. Okay. And then we have OH OH with a radical here as a reactant, but we have OH here as a product, so that's going to cancel out. That's not going to be part of the overall reaction. So let's go ahead and cross these out for just the time being. So, but we'll use them in later. But just to make sure we're keeping track of things. So if I cross this out here and here, and then the OH radical cancels out here and there. And so you'll notice here we have the HOO radical. Here and here we have it as a reactant. Here we have it as a product. So that'll cancel out. Here we have CO as a reactant, but we don't have CO as a product, so that's not going to cancel out. So that's going to be a reactant in the overall reaction. So we have CO. And we have O2 here as a reactant, but we don't have O2 here, so that's not going to cancel out. Let me fix my O2. So we'll put O2 as a reactant. And here we have NO as a reactant, but here we don't have NO as a product. We have NO2 as a product, but not NO. So that's going to be a reactant. So NO. So that's it for the reactants. Now, for the products, we have CO2 as a product, but over here we don't have CO2 as a reactant, so that's not going to cancel out. So that's going to be a product, CO2 plus, and we have NO2, and NO2 does not cancel out, so NO2 is going to be a product. So that, ladies and gentlemen, is the overall reaction from the mechanism. So all of these add up to give us this. So that's the answer to part A. Now, what about part B? Now, for part B, we're supposed to assume that the first two are fast. First two elementary steps in the mechanism are fast, the third one's slow, and we want to know what the rate law of this reaction is, the overall reaction. Well, as we said before in a previous video, when you're given a mechanism, the rate law is going to be dependent upon the slowest step in the reaction. So whatever the slowest step is, that's as fast, or that's what the rate of the overall reaction is going to depend on. So it's kind of like cars in a car jam on the highway, right? So if you've got kind of a little bottleneck going on, right, where maybe a couple of lanes are shut off, so all, like, let's say 4 lanes of highway traffic now have to squeeze into 1 lane, right? It doesn't matter how fast you are going when you're in the 4 lanes. As soon as you hit that 1 lane, you can only go as fast as the slowest car in that lane. You're not going to go past that car. So if someone's going slower than you got to go as fast as they're going, right? So your overall reaction rate is going to depend on the slowest step in the mechanism, which is this one. So the rate law is going to be dependent upon this reaction here. So we're going to start with the rate law for this third reaction in the mechanism, the third elementary step, right? So let's go ahead and write that out. Now, I did cross these out for the purpose of getting the overall reaction, but for the mechanism, for the rate law, we're not going to ignore those. So we're going to pay attention to those as well. So for this slow reaction, the rate law would be the rate is equal to K. Since this is the third one, we'll call this K3. For the forward, for this one, since this is the second one, we'll say this is 3, this is 2, this is 1. For the forward reaction, this would be K2. For the backwards, it would be K minus 2. And then for the first one, the forward reaction would be K1. And for the backwards, it would be K minus 1. So that's going to be important because we're going to be doing substitution. So we'll have to identify those Ks. Now the rate of the third reaction forward is going to be equal to the rate equal to K3 times the concentration of the two reactants in the equation, and that's going to be HOO with a dot times NO, the concentration of NO. And they all have one coefficient in front of them, so the coefficient is 1, so the power is 1 here. Okay, so we've got our rate law with respect to the third step in the mechanism. But again, when we have our rate law, we want the rate law of the overall reaction. So you'll notice here we have an intermediate species that comes from HOO dot, the free radical here. But you'll notice that's not in the overall reaction. So it should not be in our rate law. So we need to get rid of that by substitution. The NO can stay since that is in the overall reaction. So we'll keep this, but we got to substitute this one. So what we need to do is we need to go to the second step here, the second elementary step in the mechanism, and that has HOO dot in it. That has the free radical. So we can use this to help us do the substitution. Well, how is that going to help us? Well, remember, this is a fast reaction and it approaches equilibrium very quickly, right? So we can assume that this is in equilibrium, and so that means the forward reaction rate is equal to the reverse reaction rate. So we could say that the rate of the forward reaction 2 is equal to the rate of the reverse reaction minus 2. 2 referring to the fact that we're talking about the second reaction, and the positive is forward, the negative is reverse. So the forward and reverse reaction rates are equal at equilibrium. That's what it means to be at equilibrium. That's the definition of equilibrium. So now we can write out the rate law for the forward and reverse reaction. So the rate of the forward reaction of the second step is equal to K2 times the concentration of H radical, so H dot, times the concentration of the other reactant, O2. So we'll put that in there. And then we can do the reverse reaction. So the reverse rate minus 2 is equal to K minus 2. And since we're going this way, then the HOO dot becomes the reactant. So we'll write HOO dot. And that's the only one there. So this is the rate law for the reverse reaction. And since the rate 2 is equal to the rate minus 2, then therefore these two are equal to each other. So we'll substitute these in for these. So rate 2 becomes this. So we know that K2 times the H radical concentration times the concentration of O2 is equal to this here, which is K minus 2 times the free radical of HOO dot concentration. And since we're trying to substitute this, we're trying to substitute something here, we want to substitute this. So we're going to solve for HOO minus, which means we're going to divide both sides by K minus 2. So that cancels out, and we get, I'll write it over here, we get HOO dot concentration is equal to K2 over K minus 2 all over H radical concentration, H dot concentration times O2 concentration. So now that we have this equal to this and we have this, we can now substitute this in for that. So let's go ahead and do that. So we'll have the rate, oops. So the rate is going to be equal to, so we'll have K2 here, so it's going to be K3 times K2, and then we have K negative 2 on the bottom, so K negative 2 times, it's going to be H radical times O2 concentration times NO concentration. So now here's the new formula, or the new formulation of the rate law for this reaction here, based on the slowest step. Now we've got O2, which is in the overall reaction. We have NO, which is in the overall reaction. But now we have H radical that is not in the overall reaction, but it is in the first step. So now we have to do a substitution to get rid of the H radical. So now we have to do the same thing we did with the second step. We have to do that with the first step to get something we can substitute. So once again, I'm going to erase this so we can get some more space. So using the first reaction, again, since this is fast, it's going to reach equilibrium again. So this is in equilibrium, which means the rate of the forward reaction is equal to the rate of the reverse. So writing that out, rate of reaction 1 forward is equal to the rate of the reverse reaction of the first step here. So again, the rate of the forward reaction is going to be equal to CO concentration times the OH radical concentration. So that's going to be equal to, let's see here, K to the first times CO concentration times the OH radical concentration. Okay, so that's the rate. That's the rate law for the forward reaction of the first step. Now for the reverse. And now we can write out the reverse rate. So the reverse rate is the rate minus 1, negative 1 for the reverse, equals K minus 1 times, and so here's for the reverse reaction, these are going to be the reactants, so CO2 times the other reactant, so that's going to be the H radical. Oops. And so now we could set these equal to each other since the rates of the forward and reverse reaction are the same. So these are the same. So these must be equal. So we could set those equal to each other. So we could do that over here. So we have K1 times the concentration of CO times the concentration of the OH radical. That's going to be equal to K minus 1 times the concentration of CO2 times the concentration of H radical. And since we're trying to substitute in for the H radical, we solve this for the H radical. So we're going to divide both sides by K minus 1 times CO. 2 concentration. Divide this by K minus 1 and the CO2 concentration. So then this cancels out, and then you've got this equal to this. So the concentration of the H radical is going to be equal to K1 over K minus 1, CO2 on the bottom, CO concentration on top, and then OH radical. Okay, so now that we have this is equal to this, so we can take this and substitute that in for the H radical here. So let's go ahead and do that. Let's erase this. We don't need this anymore. So then this is going to be rate is equal to K3 times K2 times K1 over K minus 2 times K minus 1. And we're going to substitute this in. So this will be CO. So the concentration of CO times the concentration of, O2 times concentration of NO on the top, plus we have the OH minus, we can't forget that, so we have concentration of the OH, did I say OH minus? I meant OH radical. So we have the OH radical there, and then we have CO2 on the bottom. Okay, so now that we have this, now we can clean this up. So all of these are constants, these are rate constants, so we can just collapse all of that into one overall rate constant. So then if we clean this up a little bit, it would be the rate is equal to K. So we're just going to include all of this into K times the concentration of CO to the first power times the concentration of O2 to the first power times concentration of NO to the first power times concentration of OH radical to the first power, all over the concentration of CO2 to the first power. And then that's it, ladies and gentlemen. So in this case, you can see that there are a couple of things that are not in here. So, well, one thing anyway, we have the OH radical here. That concentration is influencing the rate. So according to this, we have OH radical and we have the CO2 as a product. So those two are indeed affecting the rate of the overall reaction. So this is the final answer based on the information we're given. So this is what we end up with after doing the substitution to get rid of the HO radical and the H radical using the first steps. I hope this was helpful. If this helped you in any way, if this made sense to you, if this was entertaining, if you enjoyed this video in any way, then please like the video, share the video, hit that like button somewhere over there. Also, make sure that you subscribe to my channel. Help me out. Hit that notification bell right up there somewhere. If you click on it, click all so you'll be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. If you have any problems or questions you need help with, put them down below. If you have a topic you want me to cover, put that down below as well. I would love to do that for you. Thanks for joining me and have a great day.